next part. In previous part, we have learned from the total frequency or overall frequency response. After that, we will go to the next section, what the PM receiver will get. So hence the signal at the receiver filter output is like that: AKHT minus KT plus VT. So there is a noise signal in the as you can find in the channel. So VT is the noise signal that is disturbed, that is not only disturbed, that is added to the total output signal. We have to extract it. We have to extract this message signal out of the noise signal. So that's at the receiver filter. So data detection is now performed by the data slicer. So data slicer is there. So data detection we can find it out from that there. So hence the signal at the receiver filter output is like that. So that is the noise signal and that is the signal output. We have to unmask this and get the output, right? Okay. So how you can get it? So just reverse process of the previous one. Okay. So that's the data detection process. So sampling YT. So we have to resample the YT, usually the optimum instant of NT plus TD. When pulse magnitude is the greatest yields. What is NT plus TD? Here you can see there is a T minus KT, right? Here you can see T minus KT. So if you just use the sampling, optimum instant sampling, means you're just replacing the T with the number of samples, total period, and the TD is the slightest change in the time domain, the phase changes. So you can easily get this. Just yield the value, you can get that. N minus KT plus TD, Vn. So Vn is the Vnt plus TD, which is the sampled noise. That means noise has been sampled. So Vn and TD is the time delay. It's a very small delay that I have told you before. It's a phase shift, is the time delay required for optimum sampling. Okay. So if you want to make the optimum sampling, you have to take the TD or delay, time delay, as you can use it here. So Yn is the compared with the threshold. This means this is sampled Yt determined by the recovered data symbol. So we have to, after getting the sampled value, we have to get back to our real value, how we get the detect the data. So now you can find out the transmitter data and transmitter symbol. Okay, so there is a symbol, is a data of 10010. But what about the plus A? After masking that, we'll get the amplitude. When it gets 0, you can get the minus A right there. When you get 1, you can get plus A right there. So that is the time period. And if you want to sample it out, here you can see all the value are aligned with the top of the x-axis. You can see at the top of the x-axis, and neither you can find out where is the minus value, is it or not. So there is an ideal sample instance. You can get the sample and the on what basis the sample occurs, highest amplitude. After that, the data slicer decision came out, and you get the data slicer, the time delay. If you add a time delay, there is a time delay data slicer. If you add it, just want to find out the sample data. So you have to check the decision from this value, whether the decision came from where is the minus A. The minus A has been coded as 0. So if we find out 0 and any kind of value will be transferred to minus A. So that is the TX symbol, okay, and that is the TX data. You have to just if the program are programmed, or there is a certain thing that has been programmed to that whenever they get the 0 binary number, so the amplitude will be the negative, that's minus A. So you can find it out. The data slicer show the negative parts or the positive parts right there. So that's the thing. So what will be the detected data? So we have to now again map this thing. When you find minus A, so it will be 0. When you find plus A, it will be 1. So after mapping, we will get the detected data, right? So that's the thing. The data collection or data detection That might be. After that, this is synchronization technique. What is synchronization technique? We need to derive an accurate clock signal at the receiver in order that we can get the YT value. In the previous section, we get the sampled value yn, but we want to find out the time domain signal YT value. Such a signal may be available directly, usually not because of the waste involved in sending a signal with no information content. Usually, the sample clock has to be delivered directly from the received signal. Okay, the ability to extract a symbol timing clock usually depends upon the presence of transitions or zero crossing in the received signal. Line coding aims to raise the number of the such occurrences to help the extraction process. So you have to extract the data. So in that process, synchronization is very much important. Unfortunately, simple line coding schemes often do not give a rise to transitions. So we need to have some line coding schemes to get the better results in synchronization and to decode some of the values or encode some of the values in digital communication systems. So that's the thing. The synchronization will also provide you some line coding schemes give rise to a spectral component at the symbol rate. There's a symbol rate. That means each symbol passes through a second. So BPF or PLL can be used. PLL means phase locked loop, and BPF means band pass filter. They can be used to extract this component directly. And sometimes the received data has to be non-linearly processed by squaring to yield a component of the correct frequency. So band pass filter, as you know, there is a simple band pass filter of the upper frequency and lower frequency. Whenever you got the data through that frequency, you will extract. So that's the you can say there is a decision part, that which data you will collect, which you will detect. So phase locked loop is the same part. That means it depends on the phase. So whenever it is 180 degree shift, it's a positive or negative, you will get the answer right there. Now, what is the intersymbol interference? That is a pretty much important part, and it's known as ISI. Okay, so these intersymbol interference is not only find out in the digital communication, in data communication, it's very much important. If you go through the fiber optic communication, through the wireless communication, that is the part of the binary data that has been transmitted through the transmitter from that will go through to the channel, and it will lay down its permanent outcomes in the or practical outcomes in the receiver side. So if the system impulse response HT extends over more than one symbol per period, symbols become smeared into adjacent symbol period. That means there is a something sample period. It may be one symbol period. That means one symbol takes how much time to transmit from transmitter to receiver. So if it's smeared, that means if there is a collision between two consecutive data, okay, that means two consecutive symbols. So that is known the inter-symbol interference. So the signal and the slicer input may be written as like that. You can write it like that, just like this. You can get the delay time and the sample noise voltage, and the first term depends only on the current symbol an, that is this first term, and the summation is an interference term which depends upon the surrounding symbols, right? So that is the intersymbol interference. But if you want to know it virtually, we will go through to this. You can see here. So there is a modulator input. Okay, so it has some HT values. You can say the HT values. Resistor capacitor first order arrangement bit duration is T. So it just the bit duration is spreaded down. It spreads because of the collision, because of the interference, because the slides are interfered with input binary 1 that is not close to 1, even not close to 1. Just it has been just behind the 1, and the time has also become delayed to 4 seconds. So for this example, we'll assume that a binary 0 is sent to 0 volt because it's less than 0, less than 1. Sometimes it is found as 0, but originally it's not 0.